Today we are going to discuss about the following problem. So we consider the minimal number of hyperplanes that are needed in order to dissect all edges of the hypercube. So just to make clear what it means. So the hypercube has 2 to the n vertices, which are just a Cartesian product of n sets of size 2, and we define the edges of this graph to connect any 2 points which differ only at one coordinate. The hyperplane is just something that is defined by a linear equation, and we say that the hyperplane dissects an edge if the edge strictly crosses the hyperplane. So if we have an edge, we want the hyperplane to really dissect the edge and not to dissect it on the boundary of the edge. Okay. So what is this number of hyperplanes as a function of the number of dimension? So let us start with an example. What happens if n equals 2? How many lines do we need in order to cut all edges? Does someone want to share? Yeah, so it's 2. We have 2 examples. We can have this thing, and we can also have another example, this one. Okay, and this is optimal. Actually, we can have this thing, I mean, the thing that goes through opposite corners, but then we cut the edges on the on their ends. So we do not allow such thing. Okay, so now let us go to n equals 3. What happens here? How many planes do we need? Yeah, so three works. We have 2 examples, as we discussed before. We can have hyperplanes that are parallel to the that are orthogonal to the axis, and we can also have like layers of hyperplanes going through different layers of the hypercube. These are the same examples from the n equals 2 case. And in general, we have that h of n is at most n because of these 2 examples. And we can ask whether this is optimal, whether h of n equals n. And the answer is no. If we go to n equals 6, then there is an example having 5 hyperplanes. And by running this example on different coordinates, if we divide the coordinates into tuples of 6 coordinates, then we can show that the in general h of n is smaller than 5/6 times n. Okay, so h of n does not equal n, and we do have that h of n equals n for small n, and h of 5 is not known in fact, but and this problem was raised in the 70s, and not much was known beyond this I mean, so we get to the history later, and now what are applications of determining this number h of n? So consider the problem of having some circuit that computes that receives n bits, x1 up to xn, and it needs to output the XOR of all the input bits. So a reasonable question is, how many gates do we need in order to implement this function? And by gates, in this context, we mean that our gates compute a threshold function of the inputs. So, for example, in this picture below, we have 3 inputs, and each gate computes any threshold function of the previous layer. And in the end, we want to compute the parity of the input bits. So we claim that once we compute h of n, then any circuit that computes parity must have at least h of n gates in its first layer. This is because if we have if we have less than h of n gates in the first layer, then 2 inputs which differ only at one coordinate must have the same value at the first layer of the computation. And because two inputs which differ by only one coordinate must have different parities, then this cannot happen. So this is one example. There are some other less direct applications for this problem, which, as far as I know, go around this problem of computing parity using threshold functions. Now let us discuss some history of the problem. By the way, if there are any questions, you are welcome. Okay, so this problem was raised in the 70s. What is h of n? So O'Neill showed that h of n is at least about square root of n. We'll see this argument shortly. Then several years later, Lond and co-authors show that if the hyperplanes have some specific form, that is, if the hyperplanes look like plus x1 minus x2 minus x3 and so forth, that is, each coefficient is either plus or minus 1, then we need n over 2 hyperplanes to cut all edges of the hypercube, and this is actually tight in a sense. So there is a gap of square root of n and n over 2. So this is a result by Alon and co-authors. Later it was shown that if the hyperplanes have the form that every hyperplane have all the coefficients either positive or negative, then also we need n hyperplanes. So we allow only these kinds of hyperplanes. and we do not allow this kind of hyperplanes. And after about 50 years, Yehuda and Yehudayov were able to show that h of n is in fact not square root of n. They showed a slightly better lower bound over h of n, and they show that this is at least n to the power 0.51, and in an informal talk I've seen they claimed to prove n into some larger power. And what we are going to discuss today is how to prove that h of n is at least n to the 2/3. I want to start with with the proof of Alon for his tight lower bound for this modified version of h of n, because I think it is nice. I mean, we will not use this kind of arguments in our proof, but I think it is good to know. Okay, so let us repeat the problem again. Suppose we are given m vectors which have coordinates plus or minus 1, and suppose this vector satisfies that for every point. Oh yeah. Is there a question? Okay, sorry. So suppose our set of vectors satisfies that for every point on the plus minus 1 hypercube, we have one of the vectors, we have one of our vectors that is orthogonal to this point. What they were able to show is that m is at least n. This is what we are going to prove. And in fact, this inequality is tight, as we'll see in a moment. So does anyone have an example for why this theorem is tight? So one example for vectors v1 up to vm is the following. So we start with v1, which is the all ones vector, except for one entry, which is -1. Then v2 has two entries, which are -1. And we go all the way until vn is the all -1 vector. So we claim that for every x, there is some vector k, so that x times vk equals 0. Why is that? Because if we define v0 to be the all ones vector, we have that x times v0 equals the sum of xi. And once we move to x times vm, we get exactly the opposite of this number. So in the middle, we had to go through 0. And this example is of size n and shows that this theorem is tight. Okay, so let us prove now the result of Alon. First of all, notice that we must have that 2 divides n. Otherwise, we cannot have that the product of, the inner product of two vectors which are plus or minus 1 will be equal to 0. So this we assume. And now we have that if we sum all coordinates of our vectors, we always get 0 modulo 2. Now we're going to partition the points on the cube into two categories. We will have the even vectors and we are going to have the odd vectors. The even vectors satisfy that the sum of their coordinates is divisible by 4. And odd vectors are going to be these points which are which have sum of coordinates not divisible by 4, which are must be 2 modulo 4. And it is easy to check that only if we take inner product of 2 vectors, we can get 0 only if we take inner product of the same time of the same type of vectors. For this reason, we are going to partition the set of vectors we are given, v1 up to vm, into odd vectors and to even vectors. And we're going to show that we have at least n over 2 even vectors, and we're going to have at least n over 2 odd vectors. So, for this, consider the even vectors, for example. And we want to prove that there are at least n over 2 such vectors. So what we are going to do now is to define a polynomial in a polynomial of x. X is as x lives on the hypercube, and we consider the product of all inner products of x with the even vectors. So if x is an even vector, what this polynomial evaluates to? Because every vector, even vector x, has some other even vector v that is orthogonal to x, then this polynomial is going to be 0 on the even vectors. So p of x equal to 0, and when x is odd, we are going to get non-zero because product of even vector and odd vector cannot be 0. We claim that if we have a polynomial that evaluates to 0 on even vectors and evaluates to non-zero on other vectors, the degree of this polynomial is at least n over 2. Because the degree of this polynomial is at most m tag the number of even vectors, we will finish the proof. So how do we show that the degree of this polynomial is at least on n over 2? So we present the polynomial p as a sum of monomials. A monomial is just the product of some of the coordinates in x. And we claim that if we use only monomials which are of degree less than n over 2, then we cannot get 0, because monomials of degree less than n over 2, when evaluated on even points, we claim that this set of evaluations are independent, linearly independent over the reals. And now we can have we can have a combination of these monomials which are zero, but we assume that our polynomial is non-zero on odd points. So our polynomial is not zero, and this linear independence will prove our claim. What we're going to show is that the monomials are in fact orthogonal with respect to the natural inner product defined over the uniform distribution of even vectors x, and this will imply that the evaluations are in fact linearly independent. And okay, so let us now let us now get to the proof. Now we show that indeed the all monomials are orthogonal to each other. So the inner product of two monomials is the expected value where x goes over all even vectors, a uniform distribution. And now because s and t are of degree strictly less than n over 2, we have that the symmetric difference of these monomials is less than n minus 1. And this inner product is the expected value of some monomial which leaves at least one coordinate of x outside. Now, by setting the coordinates that are outside s and t to be exactly the opposite of the parity of all the value of x to the power s symmetric difference s and t, we see that no matter the values of x in this symmetric difference, we can fix the other value of x to be I mean, the point is that no matter what happens in one side of x, we can I mean, if we consider x to the at these coordinates, then no matter that we condition that x is even, x has uniform distribution over a subset of the coordinates. And because we have uniform distribution over this subset of coordinates, we have expected value equal to 0. So this shows the orthogonality of the monomials and hence linear independence, and hence that the degree of the polynomial is at least n over 2. Okay, so now let us go back to our problem to determine the number of hyperplanes needed to dissect all edges of the hypercube. So I want to propose some reason for why this problem is still open for such a long time. So I want to present some barrier in order to prove that to determine the exact number h of n. So for that, let us show the first step to show that h of n is at least square root of n. The way to show that is just to argue that each hyperplane can dissect at most 1 over square root of n the number of edges of the entire hypercube. So this is a Sperner-like theorem that the largest layer of the hypercube is the middle layer, This is also equivalent to that the influence of monotone Boolean functions is at most square root of n. And this was known from the beginning about this problem. And now the obstacle to go above this lower bound of square root of n is that in fact we can define square root of n hyperplanes that dissect most of the edges of the hypercube. So in this example, if we partition the hypercube into according to the value to the Hamming weight of each point, so x are grouped by the Hamming weight of x. And so here we have Hamming weight equals 0, and at the top we have Hamming weight equals n. And now at the middle layers we have about 1 over square root of n, the number of edges in these middle layers. If we take hyperplanes that go through these middle layers, we need to take only square root of n such hyperplanes in order to capture almost all edges. And this is quite an obstacle because we can get 0.99 of the edges using only square root of n, the number of square root of n hyperplanes. So we need to somehow overcome this obstacle. And the basic ideas that we use in order to
sorry, can I ask you for one question?
Yes, sure.
If you tolerate a big enough constant and you tolerate the result starting from a high enough dimension, can you make this 0.99 closer and closer to 1? Can you replace it by something closer and closer to 1?
Yeah, so if we take so for example we can dissect 1 minus little o of 1, the number of edges, by taking only square root of n log n hyperplanes.
I see. Okay. Thank you.
So really we need to somehow capture this small set of hyperplanes. We need to somehow capture the small amount of edges that are not dissected by the hyperplanes. So this is quite a delicate problem. And the idea to overcome this obstacle is to find some distribution over edges, which is not the uniform distribution, that so that each hyperplane cannot dissect 1 over square root of n of the number of edges, but it can dissect only a smaller number of the edges. So again, we do not use the counting measure of edges, but another distribution. This is the main idea. And I want to give you some task toward this goal. So your task is to find a distribution that indeed evades hyperplanes, but only hyperplanes which are of specific form. I only want to evade hyperplanes of the form that that include only points x with specific Hamming weight. So we need to find distribution over edges that are unlikely to cross any specific set of hyperplanes. So do you have such a distribution? Now, one natural distribution to try is to choose a uniformly random layer of the hypercube. So we can have this layer with probability 1 over n, and this layer with probability 1 over n, and also the middle layers with always probability 1 over n, and just choose a random edge inside this random layer that we chose. Now, every specific hyperplane can go through only one of these layers. So if we choose a random layer with uniform distribution among n choices, then we are unlikely to be on this to be on some specific hyperplane. Okay, so let us define this distribution a little bit more precisely. So we choose a uniformly random Hamming weight W. Then we choose a random vertex on the hypercube with Hamming weight equals to W. And then we choose a random edge that is incident to X among the n possibilities. This is the distribution. And now, as we said, there is a probability of that this edge E, the probability that it dissects a specific hyperplane of the form sum of xj equals to some Hamming weight. And this probability is at most 1 over n. But I want to view this in another different way, so that that is instructive to the rest of the proof. So define V to be the normal vector to the hyperplanes we consider. And the main observation in our proof is that if we project the hyperplane H, which is defined using the normal vector V, then we will get a single point. If, however, we project an edge to the same vector V, we get an interval. When does this edge intersect the hyperplane? We have this intersection. We have this intersection only if the point that corresponds to the hyperplane belongs to the interval that corresponds to the edge. So now let us see again why the probability that a random edge intersects a given hyperplane only with probability about 1/n. So our random x that we draw in here, as if we project x on V, we get any value going from 0 up to square root of n. The length of the interval that the edge that goes from x, the length of this interval is the inner product between the direction of the edge and V, which is about 1 over square root of n. Now we have some intervals that it has lengths of about 1 over square root of n and is located anywhere in a range of size about square root of n. So how many points do we need in order to capture this random interval that has such a wide range of options? So we need a number of points to be at least about square root of n, the size of the range divided by the length of the interval. So we need about n points that correspond to hyperplanes to capture all this such a random interval. Okay, so let us now generalize this to not this specific type of hyperplanes, but to general hyperplanes. The structure of our proof is going to be as follows. So we assume that we are given hyperplanes H of L that are described by these equations. And for convenience, we assume that the normal vectors have L2 norm equals to 1. Now the first step of the proof is to define the distribution over vertices. This distribution will depend on the hyperplanes that we are given, and let E be some random edge that incident to our random vertex. Now in the second step of the proof, we'll show that the edge E projected on any normal vector V, we show that the probability that this interval contains the point H of L projected on V to be at most a constant divided by the number of hyperplanes. Now the last step of the proof is a simple union bound. We have that the probability that the edge E crosses H, crosses any H, is bounded by M. This comes from the union bound over the different hyperplanes, times the probability that the edge dissects a specific hyperplane. So this probability is bounded by one, is bounded away from 1, which means that that we found an edge E that evades all the hyperplanes with good probability. So this is the structure of our proof, and really the interesting thing is to find this distribution that evades all hyperplanes. So what do we need from our distribution? We need that the edge E projected on V, we want this interval to be short, so that we will need many points to capture this interval. And we also want that the location of the interval projected on the normal vector to have a lot of variance, so that we'll not be able to just have a random point that corresponds to the hyperplane that captures all edges. We want that different edges will go to sorry for that. We want that random edges will go to very different locations. So in this way, we will have many different intervals that we need to capture, and for this we will need many points or many hyperplanes. Now, in order to guarantee that our interval is short, we'll have the following requirement. This is only a simplification for the proof. So suppose we have the edge that goes from x to direction I, and we can see that E projected on V has length which is the i's coordinate of V of L. And the length of this interval is always bounded by the L infinity norm of the vector VL. So for that reason, we are going to assume that the L infinity norm of our vectors are about as small as they can, because we want our intervals to be short. In the full proof, we of course do not assume that, but for introducing the proof, we assume that the L infinity norm of the vectors are small. And now we present the distribution over vertices that we use in order to evade the hyperplanes. So we have all the setting summarized in here, and okay, so before we draw the vertex on the hypercube, let us start with drawing some point inside the solid cube, the n-dimensional solid cube. We will later round this vertex into we will round this point to a vertex. So we're going to use the following definition for P, the random. I mean, this is a distribution for the point P, and we will soon justify why we want this to define this point. So we take our point P to be around the middle of the cube, and around this middle of the cube we just choose P to be a random sum of the normal vectors V with random coefficients which are uniformly distributed inside some interval, and we also scale this drift from the middle of the hypercube using this scaling C that we will specify in a moment. Now we want two things from P. We want it to evade, we want this point P to be, first of all, to be inside the solid cube. This is first requirement. The second requirement is that we want P projected on any V of L to have I variance. Now let us see how we satisfy both requirements. First, for P to be inside the solid cube, we need to take C to be not too large. If we take C to be too large, then our point is likely to be outside the solid cube. Roughly speaking, the reason why C can be as large as square root of n divided by m is that each coordinate of V has absolute value, which is about 1 over square root of n. Now, once we and now we multiply this with some random value between -1 and 1. So we multiply this by something which is about ± 1. Then we multiply this by the constant c, which we assume to be at most square root of n divided by m. And then we sum over m vectors. The value of such a random variable is going to be around 1. I mean, the standard deviation of this variable is going to be 1, and this guarantees that with reasonable probability we have our point inside the solid cube. Moreover, let us now compute the projection of P on the normal vector V. So we just take the inner product between P and V of L, and we get this kind of sum, which recall that we want to show that this inner product has large variance or large standard deviation. So why does this value has a large standard deviation? So consider L equals to the L coming from V. And now in this term, we are going to have a term which is C times alpha L times 1, because we assume that the L2 norm of the vectors are 1. And so we have standard deviation of about C for this projection. And now, because we have this random interval which is of length 1 over square root of n, and it has standard deviation of its location of about C, then the probability that a specific point that corresponds to the hyperplane to be contained inside the interval is at most this value, the length of the interval divided by C. And now recall that we wanted this probability that the hyperplane to dissect the interval to be at most about 1 over square root of m, I mean at most 1 over m. Then if we substitute the value of C that we had in here, we can show that this inequality that we need is equivalent to that m to the 3f's is smaller than n over 2. And this means that this proof will work all the way up to that m is n to the 2 over 3. And so this is the sketch of the proof. And we had several things that we omitted in this sketch of the proof. So we didn't say how we round the solid cube to a vertex. So we do that in some way, and then we use Littlewood-Wofford type inequality to show that the same type of inequalities that I mean this inequality is the crucial thing in the proof, and we substitute this with a Littlewood-Wofford type inequality in the full proof. Also, we handle this. Another thing we didn't say is how to overcome this assumption that V of L infinity norm of these vectors are smaller than 1 over square root of n. So this is not very problematic that the length of this interval is, I mean the length of this interval on average cannot be too large, because if we take a random direction, then no matter, I mean, we really didn't need to assume that the infinity norm of V of L to be small in order to proceed with our argument about the length of the interval. And lastly, the most important thing that we did not discuss is, again, this problem of assuming that the L infinity norm of V of L is large. And if the L infinity is large, we cannot use such a large constant C that we used in here. And we overcome this by defining a different distribution for the random point P. Roughly speaking, we scale each coordinate in a specific way and we scale it by the maximum we can in order to have large variance for each coordinate. And this proof is decoupled with the Littlewood for the bound that we use. Okay, basically this is all I wanted to say. Maybe several open problems in this field is so now the state of the problem is that we know that h of n is smaller than a constant times n and is larger than about n to the 2/3, and there is the open problem to close this gap. Also, there is another problem of determining the number of hyperplanes needed to cover all vertices. Now, this problem is actually, I mean, it is not very interesting. We can have two hyperplanes to do that, but there are modifications to this problem which make sense. For example, if the hyperplanes are complex enough, that is, if the hyperplanes cannot use if each hyperplane must use all the coordinates in order to define this hyperplane, then this problem becomes interesting again. And also there is the notion of essential covers that is also open. So if you are interested in it, you can Google this name, essential covers. And that's all I have to say. Thank you.
Thanks so much, Ohad, for your wonderful talk. We have time for any questions people have. So I have one question. What is your sense about the amount of flexibility you have in the choice of distribution? So for instance, could there exist a distribution that's uniform on a strict subset of edges that would also suffice for this style of argument?
I guess we can have this kind of things. I mean, all we needed from our distribution is to have large components parallel to each of the normal vectors V. And we can actually do this in many ways. I mean, we did this in the most straightforward way of defining, I mean, if we want your vector to be correlated to a set of vectors, just choose your point to be a random random combination of these vectors. But yes, I guess you can do what you ask for.
Because I'm just wondering if there's a connection with coding theory. It sounds a little bit like you might want to pick a subset that's somehow like well distributed or distributed in a high complexity sense. So there are these results that say, certain computational models can't sample from good codes. This is kind of like saying, hyperplanes can't bisect a good code.
Mm-hmm.
Just a thought.
Yes, that would be interesting. Thank you. Okay, everybody, thank you very much for being in this talk.
Yeah, thanks everyone. And thank you so much, Ohad. Okay, well, if there aren't any more questions, I'll say goodbye and stop the recording.